Welcome to the 7th lecture of this course. So far we have defined a deterministic finite automaton. We have also seen a generalization of finite automaton in the sense that we allow computation to happen to go from one state to various states. So, this gives us a non-deterministic finite automaton. But the question is that how much powerful or how much extra power does that add, in the sense that whatever languages that can be computed by an NFA, can we also construct a DFA for these languages. Of course, whatever a DFA can compute, an NFA can also compute, because NFA is just a or a DFA is just a special type of NFA, where we do not use its non-determinism, where from every state comma symbol pair computation goes to a unique state. But on the other hand, given a language that is accepted by a NFA, can we also construct some DFA for that language. So, this is the question that we will try to answer, and we will answer this affirmatively by actually giving a construction. So, we will given a language accepted by an NFA. For that, we will give the construction of a DFA that accepts the same language. Okay. So, let us begin. So, as I said that every DFA is also an NFA. It is just a NFA which does not use its non-determinism. So, what we want to show today is that I will state it as a theorem. So, let n equals q sigma delta q naught f be an NFA, then there exists a DFA D. Let us give names to its tuples. D equal to q prime. The alphabet stays the same. So, we have the same alphabet sigma for the NFA and the DFA. Q prime sigma delta prime q naught prime and f prime such that L of n equals L of t. Okay. So, basically for every NFA there is an equivalent DFA that accepts the same language. Okay. So, this is what we are going to show for show next. So, let us look at the construction. So, how do we give this construction? So, before I give the formal construction, let me give an intuitive idea as to how the construction works. So, recall how an NFA actually performs its computation. In an NFA, from a state comma symbol pair, we can go to multiple states. Okay. So, I can think of the set of states that I can go to in each step as some element of the power set of the set of states of the NFA. Okay. So, basically at each step the NFA goes to a subset of its states, and a subset of Q is basically an element of the power set of Q. So, I will define the set of states of the DFA to be the power set of Q, and accordingly I will define the transition function in a deterministic manner, that given a element of that power set, it takes a symbol of the alphabet, and in the next step it goes on to some other element of the power set that is defined accordingly. Okay. So, this is how we are going to define the DFA D. So, let us look at the construction. So, as I said, firstly, the set of states of the DFA are all all possible subsets of Q. Okay. So, that is my set of states. So, I will come to delta prime in a moment. So, I will define delta prime. So, delta prime of, so for, so let A be a subset of Q, okay. Then delta prime of A comma small a. I will just come to this definition in a moment, but let us look at the other things. Q naught prime, so which subset corresponds to the start state of the DFA. So, the start state corresponds to the subset that contains the unique start state of the NFA. So, in other words, it corresponds to the subset which contains Q naught. Okay. Again, observe that this is basically an element in the power set of Q. F prime is the set of all subsets. So, let me write it as A such that A so all A subset of Q such that A intersection with F is not the empty set. So, basically I look at all subsets which contain some final state. Okay. So, that is my F prime. And now let us come to the delta prime. So, how do we define delta prime? So, delta prime of A comma A. So, basically from a set A, I want to go to all possible states that I can go to from each and every element of my set capital A. Okay. So, I look at it as the union of every R belonging to capital A of delta of R comma A. Okay. So, for every state R belonging to the set A, I look at the subset of states that I can go to on seeing the symbol A. Okay. And now I take the union over all possible R's. So, the subset of Q that I get, that is the subset that I will go to from the set of states capital A on seeing the symbol small a. Okay. So, now there is one small thing about this construction, that is what about epsilon transitions? Okay. So, in this construction we have not defined what happens if, let us say, this small a is the epsilon symbol. So, here we are only looking at small a where small a belongs to an element of sigma. So, to take care of epsilon transitions, we define what is called the epsilon closure of a set. Okay. So, let R be some subset of Q. Okay. define the epsilon closure of R as, so this is denoted, we will denote this as E of R. Okay. So, this is basically a set of states. So, the epsilon closure of a set of states is all the states that I can go to by taking one or more or 0 or more epsilon transitions. Okay. So, for every element R belonging to R, for every R belonging to capital R, I look at the set of states let's call it T, such that T is reachable from R using 0 or more epsilon transitions. Okay. So, I look at basically from every state R, I try to see if there is a path from R to T which consists only of epsilon transitions, and these paths can have 0 epsilon arrows in them. In other words, it does contain the state R itself, and I take the union over all small r belonging to capital R. Okay. So, now with this definition I define, I redefine this. So, we define delta prime to accommodate epsilon transitions. Okay. So, delta prime of capital A comma small a is union over or R belonging to A of the epsilon closures of delta R A. Okay. So, pick a state R belonging to capital A, look at the set of states that I can reach from R on the symbol small a, and now look at its epsilon closure. Okay. Look at the set of all states that I can go to using epsilon transitions after that, and now take the union over all such R's. Okay. So, this is how we define the new delta prime. So, this definition actually takes care of epsilon transitions in our NFA as well. Okay. So, I am not going to give a proof of why this construction is correct. I mean, I will just leave it at this. If you are interested, you can try to give a proof yourself, or you can also read a proof of this construction in any textbook on theory of computation. So, what I will do next is I will to understand this construction a little better, I will give an example of how this construction works. So, let us look at an NFA. So, consider the language L, which consists of strings W such that the second last symbol in W is 1. Okay. So, what would be an NFA for this? So, we saw a similar construction last time. So, we have our start state, let us call it Q0. So, on a 0 or 1, I stay at Q0. If I see a 1, I move to Q1, and then if I see a 0 or a 1, I move to Q2, which is also my accept state. So, this is an NFA which has 3 states. So, now let us try to construct the equivalent DFA for this NFA. So, the way I will construct the corresponding DFA, I will not list out all the 8 states. So, this NFA has 3 states. So, the power set will contain 2 to the power 3, that is 8 states. So, instead of listing out all the 8 states, I will do them in a phased manner. So, I will only write down a state when I require it. Okay. So, what would be the start state of the DFA? So, the start state of the DFA by definition is the state which contains Q0. So, I will just denote it with let us call it let us call it 0. Okay. So, this is my start state. Now, what happens at Q0? At Q0, if I see a 0, I stay at Q0. Okay, I stay at only the subset Q0. So, I will do a similar thing here. Okay. So, I will just change this a little bit. So, just to avoid confusion, let me call this state Q prime 0. Okay. So, if I see a 0, I stay at Q0. What happens when we see a 1? So, when we see a 1, we go to 2 states Q0 and Q1 simultaneously, or in other words, we go to the subset Q0 comma Q1. Okay. So, I will denote that using the notation Q prime 0 1. So, this is the subset which contains 0 and 1. Now, let us look at this subset. What happens from Q01 when we see a 0? So, once again we have recall that we have to take the union. So, from Q0 when we see a 0, we go to Q0. From Q1 when we see a 0, we go to Q2. Okay. So, if I take the union, it is Q0 Q2. So, from Q01, if I see a 0, I will go to the state Q prime 0 2. Okay. Once again, from 0 on a 0 I go to 0, from 1 on a 0 I go to 2, hence it is 0 2. What about from Q01 on a 1? So, from Q0 on a 1, okay, let me write it here. So, from Q0, if I see a 1, we go to Q0 and Q1, and from Q1, if I see a 1, I go to Q2. Now, if I take the union of these two sets, I get Q0, Q1 and Q2. So, that state is not present here. So, I will create a state corresponding to that. So, Q prime 0, 1 and 2, and from Q01 I go to this state on the symbol 1. Okay. Now, I need to draw transitions for these two states as well. From Q02, if I see a 0, so observe that from Q0 if I see a 0, I go to Q0. From Q2 if I see a 0, I do not go anywhere. So, it is the empty set. So, therefore, the union of the empty set and Q0 is only Q0. Hence, from Q02, if I see a 0, I go to Q prime 0. What about 1? From Q0 if I see a 1 I go to Q0 and Q1, and from Q2 if I see a 1 I go to the empty set. So, the union will give me the following, that from Q02 on a 1 I go to Q01. Okay. So, that completes the states Q0 prime, Q01 prime and Q02 prime. Now, what about Q012 prime? Again let us analyze. So, from Q0 on a 0 I stay at Q0, from Q1 on a 0 I go to Q2, and from Q2 on a 0 I go to the empty set. So, basically from Q012 on a 0 I will go to Q02 prime. Okay. Similarly, on a 1 from Q0 I go to Q0 and Q1, and from Q1 I go to Q2. So, therefore, from Q012 on a 1 I stay at Q012. What are the accept states? So, the accept states will be all states that contain some accept states. So, the only accept state of my NFA is Q2. So, this will be an accept state because this contains a 2, and this will be the other accept state. Okay. So, now you can see that although if I look at all possible 8 subsets of 0, 1 and 2, I also get other subsets. I mean, I also get other states like for example, Q. So, we have 0, we have 0, 1, we have 0, 2 and 0, 1, 2. So, there are other subsets like only 2 or only 1, okay, or the empty subset, but we do not bother about those subsets because those subsets are not reachable from the start state. Okay. So, these are the only 4 states that are reachable from the start state, and this gives the complete DFA. Okay. So, let me mention it here. States that are not reachable from the start state are known as dead states, okay, and we do not need to show them in our construction of the DFA. So, this is the example. So, now let us come to let us come back to the topic of regular operations. So, we defined the 3 regular operations: union, concatenation and star. We will see why these operations are called regular operations. In other words, what we will show next is that if, so let me state this. So, if L1 and L2 are regular, then L1 union L2, L1 dot L2 and L1 star are also regular. Okay. So, this is not very difficult to show once we make use of the fact that a language is regular if and only if there is some NFA for it also. So, our actual definition of regularity was via DFA, but because we have just shown that DFA and NFA are actually equivalent. So, therefore, for every regular language we can assume that there is a corresponding NFA for it. Okay. In addition, what we can also assume that there is an NFA which has a unique accept state. So, the reason why we can assume this is because if there is an NFA with multiple accept state, I can create a new accept state and put epsilon transitions from all the old accept states to this new accept state. Okay. So, for a regular language, we can assume that there is a NFA accepting it with a unique accept state. Okay. So, let us look at the proof of this theorem. So, the proof is again not very difficult and it follows through construction. So, L1 is regular. So, for the language L1, let N1 be a NFA that in fact, let me just write it as a table. So, we have our language L1. So, for language L1, let N1 be the corresponding NFA for it, which has start state, let us call it Q1, and accept state R1. Similarly, for the language L2, let N2 be an NFA that accepts it with start state Q2 and accept state R2. Okay. So, to be more precise, L1 is equal to L of N1 and L2 is L of N2. So, how can we construct an NFA for L1 union L2? Okay. So, observe that if I construct an NFA, so let us say that this is my NFA N1 with Q1 and R1, and this is my NFA N2 with Q2 and R2. If I create another NFA which has, let us say, start state Q and accept state R, and I add epsilon transition from Q to Q1, Q to Q2, and from R1 to R and R2 to R, every string that is accepted by N1, I can basically take the computation from Q to Q1 to R1 to R, and every string that is accepted by N2, I can take the computation via Q to Q2, from Q2 to R2 and then from R2 to R. Okay. So, every string that is there in one of the two languages is there in this NFA. Okay. So, this is a NFA for L1 union L2, which proves that L1 union L2 is also regular. Similarly, for concatenation, so let me just state it here. So, this is the NFA for L1 union L2. Similarly, for concatenation, we have N1 with Q1 and R1, and we have N2 with Q2 and R2. I add a state Q with epsilon transition from Q to Q1. I add an epsilon transition from R1 to Q2, and I add a state R with epsilon transition from R2 to R. So, every string that can be written as a concatenation of two strings such that one is accepted by N1 and the other is accepted by N2 is accepted by this NFA. Okay. So, this is basically an NFA for L1 concatenated with L2. Finally, for L1 star, if I, so let us say this is my NFA for L1 with Q1 and R1, I create a new start state Q and I create a new accept state R, and I put an epsilon transition first from R1 to Q1, I put an epsilon transition from Q to Q1 and from R1 to R. Okay. So, look at any string that is there in L1 star. So, if a string is there in L1 star, it can be written as a concatenation of strings each belonging to L1. So, each of those strings I can accept by going from Q1 to R1 for the first string, taking epsilon transition back to Q1, again going from Q1 to R1 for the second string, and so on. Similarly, every string that is accepted by this NFA can be written as a concatenation of strings each belonging to L1, hence that string belongs to L1 star. Okay. So, therefore, this is a NFA for L1 star. Okay. So, this proves that the languages L1 union L2, L1 concatenated with L2 and L1 star are also regular. Okay. Thank you.